After revising windbreaks, we will talk a little bit about temperature manipulation. And you already know that temperature is very important for many processes of the plant or the soil, like seed germination, plant emergence, development, growth, assimilation, in other words, photosynthesis. It also, temperature of the soil affects very much the root distribution. So if the soil is very cold, the roots will be only distributed in the upper layers. But temperature also affects very much the symbiotic nitrogen fixation of legumes. It affects photosynthesis and also water uptake. Why? Because it affects water viscosity, and we also know that it can affect the root permeability. Temperature is also important to determine the rate of mineralization of organic matter in the soil and also for soil respiration. So, temperature is very important for soil processes and crop processes that determine crop productivity. But in the open, we have little to do to improve the temperature of our crop. In principle, we can use the slope and the aspect means the orientation of the land, to improve temperature. How? Well, you know that the angle of incidence of radiation on a surface determine the irradiance on that surface. So if the surface is perpendicular, is normal to the solar beam, we will have a maximum heating of the soil. The efficiency of the slope and aspect to determine soil heating depends on the fraction of diffused radiation and on the zenith angle. If the fraction of diffused radiation is low, then the slope and aspect has very little effect on soil heating. Why? Because radiation is coming from all the sky, all radiations, all directions, excuse me. It also depends on the zenith angle. If the zenith angle is very small, in other words, if we have the soil on top of our location, if the soil is oriented to the south or to the north, it doesn't matter. So the highest effect of slope and aspect will occur on soil temperature will occur for mid-latitudes and especially during the spring and the autumn. The effect will be less important close to the equator or for very high latitudes. And the effect will be also less important during the during the winter, because the fraction of diffused radiation during winter is very high, and also during the summer, because the zenith angle during summer is very small. Here you can see the effect of orientation and aspect on the temperature of different locations in a ridge field where we have ridges and furrows oriented north-south. You can see that the highest temperatures occur on the west side of the ridges. The lower temperature during the night occur on the ridge specifically, and the higher temperature during the night occur in the furrow. We see also that during the morning, the east side of the furrow has higher temperature, and during the afternoon, the west side of the ridges has higher temperatures. To change or to manipulate the soil temperature, we can also use mulches. And mulches are barriers that affect heat or water transport. Many times mulches, the role of mulches is for soil protection against erosion or for weed control. We can use as mulches with residues, straw and crop residues. We can use inorganic products like plastics, gravel, or sand, and we can also use industrial byproducts like bark or wood chips. You can see bark frequently on gardens as mulch for weed control. In the case of plastics, the main effect of the plastic, or one of the important effects of plastic, is that we reduce evaporation. A secondary effect, very frequently used in agriculture, in horticulture, is that the plastic prevents the contact of the plant or the fruits of the plant with the soil, and that prevents some diseases. Black plastic is typically used for weed control, for instance, in the case of strawberry crops. On the other hand, transparent plastics are the best alternative for increasing soil warming during the spring. The contrary effect is that of straw or residues that delay soil heating during the spring. Here we see some data, some measurements that we did in Cordoba, comparing a bare soil, this green line, with a transparent plastic, where you can see that the temperature increases during the daytime as compared to the other, and a black plastic. The black plastic doesn't heat much during the daytime, but also has lower cooling during the night. The reason why this transparent plastic cools down as bare soil is because it is not trapping infrared radiation, while black plastic is capturing a lot of long-wave radiation. That's why the transparent plastic cools down the soil the same as with bare soil during the night. As I said, the presence of residues that are used in the so-called conservation agriculture, where we keep the residues and we plant the new crop on top of the residues, the presence of residues on the soil surface means that when we plant during the spring, we have a slower soil warming, and thus we can have a delay in crop development. This graph shows the mean soil temperature in the surface of a bare soil during the spring compared to a soil covered with residues, the red line. We see that the difference is important, up to 4 or 5 degrees in many days. That implies that when we are doing conservation agriculture, we can have a slower development of our crop during the spring. In very special cases, like in the case of nurseries to produce plants that are later transplanted, or in sport stadiums, imagine Santiago Bernabeu, we can use artificial soil heating. That is so limited because of the high cost. At a smaller scale, like in nurseries, we can use electrical resistances that are buried below the soil. Larger scales, people have used pipes with hot water. The cost of that is more affordable when we have some availability of hot water as a byproduct of energy plants or some industries. Well, apart from changing the slope or the aspect or using mulches, there is a possibility for cooling the canopy by sprinkling irrigation on top of it. It is possible to calculate using the formulas that you can find in the book in chapters 4, 5, 6, 7. We can calculate the decrease of temperature of a wet crop compared to the same crop when it is dry, using meteorological data like net radiation, vapor pressure deficit, etc. I'm not going to stop here to derive this equation. If you are interested, you can read it in the book. But the idea is that the cooling due to wetting of the canopy is proportional to net radiation, to vapor pressure deficit, and to canopy resistance. Remember that canopy resistance is the average stomatal resistance. So this method for cooling down a crop canopy will not work if the vapor pressure deficit is low, for instance, in very humid areas. Okay. We have seen that there are very little things that we can do in the field to change the environmental conditions of the crops. We can put windbreaks, we can use mulches, and we can even change the energy partitioning of the crop by using irrigation. But in some situations, we can afford using more sophisticated structures like greenhouses. There is a wide range in the level of control provided by greenhouses. The two extremes would be the simplest case is that of plastic unheated greenhouses, like those of the Parral type that are typical of Almeria. They don't use additional light or additional heat in general. The most sophisticated greenhouses can be found in Northern Europe, like in the Netherlands, where they use additional light. They use lamps to provide additional light. They use heating systems, and they can use also additional CO2. They can provide CO2 fertilization. This is an aerial view of the greenhouses in Campo de Dalías in Almería. And this is the view of a greenhouse in the Netherlands with additional lighting. One thing that we have not commented during this lecture is that typically we consider the environment by looking at the data that the environment for the crop by looking at the data that we measure in weather stations. It is possible to calculate the temperature of the crop using the values that we measure in the weather stations. For instance, in the case of frosts that we will be talking about in the second lecture today, When we have 0 degrees measured in the weather station, in a shelter, with a shelter instrument, when the conditions at the weather station are of 0 degrees, the values that we can observe for different crops and different conditions would be as follows. Imagine that we have a short crop, like a grass, or a tall crop. For instance, let's consider a wheat crop, in a tall wheat crop with a height of 1 meter. If the conditions are cloudy or clear, or if the relative humidity is 70 or close to saturation 100%. If we have a short crop with cloudy conditions and 70% relative humidity, the temperature of the crop surface would be minus 1.4. If the conditions are clear sky, when we have 0 degrees at the weather station, the temperature at the crop surface will be -4, around -4 at the crop surface. This is a short crop. If the crop is higher, like here, the drop in temperature would not be that important. We would measure -2.5. If the conditions are of higher humidity, the drop in temperature would not be that important. Would be -2.4 for a short crop and -1.3 for a tall crop. This is only an example. This is not only, this doesn't mean that you would always see something like this, but it is indicative of the differences in temperature that we would find between the air temperature that you measure at the weather station and the crop temperature that you measure in the field. Apart from calculating the minimum temperature, we can also calculate the maximum crop temperature as a function of air temperature measured at the weather station. For that, we need to consider the evapotranspiration and the wind speed and use a formula like this one. Temperature at the crop surface is equal to the air temperature plus 1 minus Fg multiplied by net radiation minus evapotranspiration, latent energy flux. Fg is the fraction of net radiation used in soil heating. For instance, we can take a value of 0.1 for this parameter. And here, Ra is the aerodynamic resistance. Well, ρ, air density, and Cp, heat capacity of the air. Look at this. The difference of the crop and the air temperature is proportional to radiation. So the more radiation, the warmer the crop will be as compared to the air. And it is inversely proportional to evapotranspiration. The higher the evapotranspiration, the lower the difference between the crop and the air. So we can even have the crop being cooler than the air if the evapotranspiration is high. On the other hand, if we have water stress and evapotranspiration is small, then the crop temperature will be higher. What happens with wind? If we have a high wind speed, then the aerodynamic resistance is low. And if the aerodynamic resistance is low, then the difference between crop and air temperature will be small. On the other hand, if we don't have much wind, if the wind speed is low, then this aerodynamic resistance will be high. And if this is high, then the crop will be much hotter than the air. So, in summary, the crop temperature will depend on the maximum air temperature, on the evapotranspiration, and on the wind speed. To have very high crop temperatures will occur when evapotranspiration is low and when the aerodynamic resistance is low. In other words, and when aerodynamic resistance is high. And that occurs when wind speed is low. Taking into account also the energy balance, we can evaluate the difference in temperature inside and outside unheated greenhouses. This simple equation, which derivation you can find in the book, tell us that the difference in temperature between inside and outside is proportional to solar radiation inside the greenhouse and is inversely proportional to the height of the greenhouse and to the relative renovation rate, cubic meters per air per cubic meter of greenhouse per hour. So how can we increase the difference between temperature inside and outside of the greenhouse? By increasing the radiation inside the greenhouse. How can we reduce the difference in temperature? By reducing the radiation inside. And that is made by using shade cloths or using some type of paint to reduce the transmissivity of the glazing. To reduce the difference in temperature inside, outside, we can also increase the renovation rate. We can open the vents, open the windows of the greenhouse, and that will increase the renovation rate, and that will decrease the temperature difference between the inside of the greenhouse and outside conditions. Okay,